This recording is discussing a simulation that's online that does a great job simulating gas particles. It's through the Colorado University. I typed into Google PHET. I don't know what that stands for, but then gases. And this came up. PHet, we'll call it colorado.edu. We'll click on that, and you don't need to download anything. I think I'm using Chrome browser. You can just click on that arrow and you get this simulation starting point. And I'm not sure what these do, but we're going to click on ideal because it just does a great job of relating pressure, volume, pressure, temperature, and we of course have to have some molecules in this open space. So I'm going to pump in just one pump, squeezing it in. And we've got about 50 gas particles now moving in this box. I'm going to expand the box out. You can grab this and make a bigger volume, and try to just kind of relate some of these properties, volume to temperature to pressure. Now we have some certain number of molecules in there. And I can now take and consider this volume and say, okay, what happens if I take and make this volume half the size or less? The speed of these, I guess, is not going to be increased. We're going to talk more about that later, I guess, in this video. But I'm just going to say, let's say the volume was this amount, and then same balls were in a volume much smaller. Watch what happens to the pressure. At 3.0 atmospheres is what we are at right now. It's kind of bouncing around. We'll say 3.0, high is 3.5. But when I bring this in and we consider now a new volume, please do not consider this to be sort of as I'm doing this, molecules are being pushed to the right. We're just going to say it's about a third. So we're expecting that the pressure should go up because the same number of balls, about 50, now have to be in a smaller space. So watch what happens to that pressure. It went from, about 3 to about 3 times that because we cut the volume by a third. So there's an inverse relationship. The smaller the volume, the higher the pressure. So we go the other way, so it's about 9. But if I triple that, it's going to be about 3 now, and you can play around with that. Now one thing to notice is the temperature is pretty constant, 300 degrees Kelvin. Bring the pressure, bring this back in, 300 degrees Kelvin, and we're going to talk about that at the end of this video as a kind of a question. So there you go, that's volume to pressure, an inverse relationship. Now we can, I guess, look at what happens if we increase the average energy of these gas particles. We do that by heating it. So I can do that here on the bottom. I went down to 289. Let's go back to 300. So at 300, we have a certain speed of these balls, but we can increase their speed or slow them down. I'll go slow. We'll cool them down to about 200 degrees. So we've done that, it's close enough, and we notice that our pressure was about 9. Now it's down to 6, 7 atmospheres. And so the balls have moved more slowly now because we're cooling them. This is just a simulation. Air molecules move about 1,000 miles per hour, so it's just not to scale, so to speak, or whatever. But pressure, what we're measuring is in relationship to temperature, the speed at which they're hitting that diaphragm that causes the needle to move. So I've slowed them down, and therefore, even though they're higher concentration, they're just not moving as fast. But if I expand it out, it's even going to go down even more because now the number of them hitting this diaphragm goes down. So the number of them in this space, they're all now spread out, so we don't have as many hitting that diaphragm. So you can maybe go like this, using some audio simulation here. Tink, 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 tink. That'd be kind of the number of hits, but if I decrease the volume, we can say tink, 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 tink. It's hitting more often, this diaphragm, because there's just less space for those gas molecules to be expressed in. So we can say in this case, as far as relationships, we saw that the expansion of the volume decreased the pressure. Expansion of the volume decreased the pressure, so it was an inverse relationship. But there's a direct relationship between temperature and pressure. If I increase this now and go way above 300, we're going to go past that 9. We're going to go probably up to 12, I'll say, something like that. So yeah, we're around now. The number of collisions is faster because they're moving more. They're the same concentrate, same volume, but as I increase the temperature, they're just moving faster. So of course they have more ting 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 hits on that diaphragm because they're now moving faster and giving more energy to that diaphragm because they are not only one hitting it more often, but they bring more velocity. So there's a lot of things going on there. So take home message is if you increase the temperature, it's a direct relationship, you increase the pressure. So we saw keeping it constant at some temperature, we can have the inverse relationship. Volume increases, then the pressure drops. Volume decreases, and the pressure increases. So inverse relationship between B and P, volume and pressure. But a direct relationship between temperature and pressure. And of course, I don't need to simulate this one, but if we pump this more gas, of course, there's going to be just more collisions. Same speed, same amount of energy with every ball hitting this diaphragm, but there's just more of them hitting that diaphragm. Hey, one last question to leave you with. So this is interesting. In physics, we learn that work is important. So if I expand this out, this volume, and I think of it as in this particular state, I have all these balls bouncing around. If I have a uniform motion, I'm working against those collisions on this wall that are pushing against me. I push against them. I would add energy to all these spheres that hit the surface because if I move it in just a little bit, that velocity of moving in is transferred to the balls. So we'll watch the temperature here, 392. 392. We're going to, I guess nothing else is changing. I'm not adding number of balls. It's not going up. So 392 is still 392. That's strange. Give me some comments in my YouTube video as to why that's strange. Because if we consider those balls and in process, not this state and then all of a sudden we just jump to this state without any sort of connection, but to get from this expanded state to the third of a volume state, I pushed. And it's hitting all those balls. So 392, what would you expect to happen to the temperature if you're working against the gas? So therefore you're transferring energy to them because energy is conserved. So I work, I expend, I lose, but they gain. Shouldn't the temperature, well, you tell me, should it increase or decrease? That's interesting, this simulation. As you use it, some of the things you notice. Comment, if you could, in the comment box below the YouTube video. Why would the temperature change, and what would that temperature change be? Thanks. Bye-bye.